Um, Last class, we started talking about vectors, and that's what the lab this week is connected to. Um, so today we're going to start talking about how to use that vector idea with the kinematic quantities that we need, the directional ones, which are position, velocity, acceleration mainly, and then also displacement. So now we're going to get into, we're going to use vectors for 2D kinematics. So I'm going to start by defining the position vector. Then I'm going to do velocity. Then I'm going to do acceleration, just the same way that I did with one dimension. Okay, so in 2 dimensions, so say you have an object. So in 1D, the object we were talking about was a train. So I'm going to draw a train again. But now it's in 2D. So it's not confined to a train track anymore. So let's see. Okay, so now it can fly. Okay, it's just a flying train. And what does it take to define the position? So the idea is now this train doesn't go along a track and it doesn't have 2 choices of directions. It has infinitely many. It can go straight up, straight down, anywhere around it. So how do you use this vector idea to define the position as a vector? And anybody remember what the steps were for defining the position in 1 dimension? So so in 1 dimension, a directional quantity is a signed number, right? It can be positive or negative. So before, and there was a train up there, it went along the tracks, but we couldn't assign a number to it until we did 2 things. What were those 2 things? Yep, we had to define a 0 position and a positive direction. Okay, and there's a perfect analogy between that in 1 dimension and what we have to do in 2 dimensions too. So now, instead of a 0 position, we have to choose a coordinate system origin location. And instead of choosing a positive direction, we have to choose what the orientation of our coordinate system is. So once we've done those 2 things, we have to choose the origin location. That's like the 0 position. And we have to choose the axis directions. That's like choosing the positive direction in 1D. But once we do that, so we're still talking about particles. So even though the train is however many meters long and whatever, we're not dealing with treating the train like it occurs at a single point. So we have to choose a point on the train to specify its location. So that's what that center of mass symbol means. And now the position vector is a vector that goes from the origin of the coordinate system to the object. So this red vector is the position vector. Um, and if you know, if you specify this as, um, a magnitude of the vector and an angle from some landmark, from the horizontal or the vertical or something, you can take this vector and express it in components, and then you can do math with the components. Um, but you can't specify that vector until you make these two choices. So um, these together are what I'll often call choosing the coordinate system. It's sort of choosing two aspects of the coordinate system. But I want to bring out the fact that it's two separate things that you're choosing, because really, like conceptually, they're the same things that we had to choose in 1D. And I'm going to say coordinate system a lot, so I'll just abbreviate that. Um, the units for the position vector are the same as in one dimension. It's units of length. And so the SI units are meters. And then just like we did in 1D, we can use the idea of position to define the velocity vector. Um, so the velocity measures how quickly the position is changing. Um, and the way I did it in 1D was I first defined average velocity, and then I described that sort of pinching idea where you pinch closer and closer to the point that you want to define the instantaneous velocity. It works just the same way here. So the average velocity, and it's a vector, is equal to position at the later instant minus the position vector at the earlier instant divided by the elapsed time. And then in the limit, as T1 and T2 get closer to some desired time T, um, V average gives V instantaneous. Um, in 1D, you could think of, you know, before I go on, I guess, this is the one that we care about. And so whenever I just talk about the velocity, um, I'm talking about instantaneous velocity. If I want average, I'll specify that. Um, so in 1D, you could think of the velocity as being a combination of two things: a magnitude, which is the absolute value of the velocity, that's the speed, okay, and then a direction that was given by the sign. Okay, if the thing's moving in the positive direction, the sign's positive. If it's moving in the negative direction, it's negative. Um, it's going to work just the same with the vector velocity. The magnitude of the vector, remember, so that's the length of the arrow, the length of the vector. The magnitude is the speed. So no matter what direction you're going, in a car, the speedometer tells you the speed. And that speed that your speedometer tells you is the magnitude of the vector, the length of that vector arrow. Okay, so notice. So first, the velocity vector is made up of two things. All vectors can be broken down into a magnitude and a direction. The first one is the magnitude, which is the object's speed. And the second one is the direction, which is the direction the object is moving at that instant. The second thing that we're going to use a lot is, so what happens in 1D if you shoot an object up into the air? We use something about the velocity to specify when the object got to the highest point in its path. What was that in 1D? When the velocity is equal to 0. And so in 2D, your first thought, sort of a natural first thought, would be the thing has reached its highest point when it's moving in 2 dimensions if the velocity vector is equal to 0. That's not quite right, but it's the right idea. Well, so if something is launched out at an angle, if we have the y-axis pointing up, which is how we're going to always do it in free fall problems. So if the y-axis is up, then an object reaches the highest point in its path when the y component of the velocity is equal to 0. The x component won't be 0 in general, but the y component will be. When the y component of the velocity is 0, you could also write that as v sub y is equal to 0. Okay, so we're going to use that a lot. And then the last thing is with velocity. So you can do this with any vector. We were talking about that last time, that if you know the magnitude of a vector and you know the angle between the vector and some, vertical or a horizontal or something, you can calculate the components as the length of the vector, the magnitude of the vector times cosine and sine of the angle. Velocity is the one that usually it's going to be the only one that we're going to have to use that information to calculate. So often we're going to need calculate the components of the velocity vector um, from the object's speed and its angle. For example, you'll see problems that say stuff like an object is launched with a speed of 20 meters per second at 20 degrees above the horizontal. So what that's saying is that the instant that the object is launched, if this is the horizontal, the velocity vector has a magnitude of 20. Bless you. It makes an angle of 20 degrees above the horizontal. And so if you use a coordinate system like this, then at that instant, the velocity vector is 20 times cosine of positive 20 degrees, 20 times the sine of positive 20 degrees, and that gives you a velocity vector um, of 18.8, I think. And then this one is 6.84. Okay, so a lot of times you'll be given information like the speed and the angle, and you'll have to come up with the components. And the reason that you have to come up with the components is because to do math with vectors, you want the components. That was a big part of what we talked about last time. Any questions about velocity? Yes. Okay, so well, we haven't really done enough yet to calculate that, but all that's saying is at the instant it's launched, which you can imagine you would call your time equals 0, your initial velocity vector is 18.8, 6.84. The acceleration of gravity is going to be downwards at 9.81. And so you'd use all that stuff, put it into the constant acceleration equations for 2 dimensions, calculate where the y component of the velocity is going to become 0, and then you'd use that to figure out the position. And we'll do a lot of problems like that, but we haven't quite gotten everything yet. Any other questions? Okay, and the last thing we have to define is acceleration. Um, and acceleration is a measure of how quickly the velocity is changing. Um, in 1D, there was kind of only one way, in a sense, that the velocity could change, and that is the speed can change. Um, so there's only one way in 1D that velocity changes, and that is that the speed changes. There's a new thing in 2D that was not a thing at all in 1D, and that is that, so remember the velocity vector has a magnitude and a direction, okay? Now, for the first time, we introduce the idea of turning. Um, and if the direction of the velocity vector changes, well, then and if the velocity vector is changing, then you're going to have acceleration. And so in 2D, acceleration is both speed changing and or turning. And in labs, we're going to spend a lot of time on identifying the part of the acceleration that comes from each of these. Um, it's not going to be as big a deal in the class where we're talking about doing calculations, but this is a new thing. And as an example of this, um, think about like those that thing that they always show in astronaut movies of like people um, sitting in this chair that like spins around really fast. This is how you can tell it's an astronaut. Okay, so this thing uh, whips around this circle, you know, um, and they use this setup to get people used to very high accelerations. Um, in 1D, the only way that you can have high accelerations is for the speed to change really quickly. But imagine how this thing works. Once it gets up to speed, it starts at rest and then they speed it up until it's going pretty fast. But once it's going, there's no change in speed as the astronaut goes around this circle. The astronaut's going at whatever, 20 meters per second or 30 meters per second or whatever the whole time. The reason that that's a high acceleration is because the person is changing direction really quickly. And that change in direction causes an acceleration the same way that if you're moving in 1D, there's an acceleration if the speed changes. So this astronaut is accelerating even though the speed is constant. And you know that feeling like if like from Valley Fair or whatever, if you're on a ride that you can imagine, well, what's the one, the Enterprise? Anyone ever been to that? Is there still such a thing as Valley Fair? Okay, good. But the Enterprise is this thing like you sit and it makes you do like giant backflips, And the speed isn't changing, but your direction is changing, and that's why you can feel the acceleration. I guess same with any kind of, well, there are a lot of rides that use the fact that you're changing your direction fast to cause an acceleration, even when the speed isn't changing that fast. Um, so there's a big acceleration, even though the speed isn't changing. And that's because the direction is changing. Uh, or let me just say, because of turning, that also requires acceleration. Um, okay, so now we need to talk about the constant acceleration equations, and they look pretty much the same as they did in 1D, except now we have to break it up into components. So the constant acceleration equations, so remember in 1D, we had this first one that said V final is equal to V initial plus the acceleration times time final. In 2D, that equation still holds, except all of the things that are vectors, we're talking about the x components of the vectors. And then it also holds, but talking about the y components. So we also have vfy is equal to viy plus ay times time final. Yes. Time is not a vector. So remember, time in 1D wasn't a directional quantity, and it's not a directional quantity now either. So there's still just, time meant the same thing now that it did in 1D. And then the second equation that we had in 1D said P final is equal to P initial plus V initial times time final plus 1/2 A times time final squared. And again, this equation holds with all the directional quantities being x components of vectors. And it also holds with each one of those being a y component of a vector. Yep.
So when you have the x and the y, you have to do like when you do one, you have to do the other one too.
You don't have to, nope. So just like, remember, and I'm going to go through a set of steps the same way I did in 1D. But remember, uh, one of the steps in the 1D process for solving 1D problems was you write out all your variables and then you look for one equation that works. And if you find one equation that works, that's all you need. And it's true here too. These are all true all the time if you have constant acceleration, but you're just looking for the ones that help you. And then the last one said 2a times the quantity PF minus P initial is equal to VF squared minus V initial squared. And that one holds for X components of vectors. And then it holds for Y components too. Okay, so it's 6 equations now instead of 3 equations. They're not really any harder to remember if you just understand that pattern, that we're talking about the same 3 equations, but you have to separate directional variables into X's or Y's. Yep. Okay, so that's what we're trying to work towards because it's a more of a bookkeeping issue now. So the first thing to notice is uh, there's a much bigger set of possible variables you have to deal with. Um, so remember let me put a box around these because these are really important. Okay, so in 1D, to use the constant acceleration equations, we had that list of, I think it was 6 variables: time final, acceleration, P initial and P final, and then V initial and V final, 7 variables. Okay, we can make a list just the same in 2D, but all those directional variables have 2 components. So now we have time final, acceleration, but that's broken down into X and Y components, initial position, X and Y, final position, X and Y, um, and then initial velocity, X and Y, and then final velocity, X and Y. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we're still just going to have to go through that list of variables one by one, thinking about which ones we know, which one we're trying to calculate. But it's, obviously a little more time consuming now. So now, based on all this stuff, let me list out a general set of steps that you can follow to do these problems, and then I'll just start getting into examples, and we'll do examples for probably like a full class. So these are general steps for two-dimensional constant acceleration problems. Um, and all of these steps are kind of modified two-dimensional versions of the steps that we used in one dimension. So I think with a lot of this stuff, if you can figure out the connections between 1D and 2D, you can store the approaches in sort of the same part of your brain. So don't think of this as like all new stuff. Think of it as just sort of an extension of the stuff that you've already been spending a lot of time on. Okay, so the first thing you have to do, well, what was the first thing you had to do with one-dimensional constant acceleration? That's right. So you had to choose your instant for time equals 0 and time final, and then you had to choose your 0 position and positive direction. Um, and this is just like that. You have to choose your time equals 0 instant, your time final instant, and then you have to choose your origin location. That's two-dimensional version of uh, your 0 position, and you have to choose the coordinate system orientation. That's the two-dimensional equivalent of choosing your positive direction. And these two together, a lot of times I'll just call that choose your coordinate system. But there are two parts to choosing a coordinate system. One is the orientation of the axes, and the other one is where you put the origin. The next step is to list out the variables you know and the variables you want. But now there's a whole bunch you have to deal with. So this is out of that whole list that we just came up with. Time final, acceleration, x and y, key initial, x and y, key final, x and y, v initial, x and y, and v final, x and y. And once you've done that, look for an equation out of the 6 that I gave you. It has to have the variable that you're looking for. It has the variable you want. And where every other variable is known. That's exactly the same as it was in one dimension. Just now you have 6 equations to pick from. And then there was one more step in one-dimensional motion. Anyone remember what the last step was? I think it called it step like star or something. It wasn't even numbered because most of the time we didn't have to deal with it, but sometimes there was another step. Yeah, that's right. So sometimes, occasionally in one dimension, no equation worked, and then you have to choose an intermediate variable, and that intermediate variable is going to be in one dimension most of the time final or acceleration. It's going to happen more often in 2D. So I'm going to call it step 4. And if no equation works, find an intermediate variable. And the good news is this intermediate variable is almost always going to be time final. And then go back to step 2. Okay, so why is it that it's almost always going to be time final that you're going to look for in 2 dimensions? The answer is, if you look at these equations, so look at each pair of equations, like matching equations. So is directional variables occur in pairs, an x and a y component. And the bad news is that there's no defined relationship between the x and y components of a variable. So knowing the x component of the final velocity doesn't tell us anything about the y component of the final velocity. But there's one thing that crosses over between these x equations and these y equations. There's only one thing, and that's that time final, since time is not a vector, the time final that you get there, you can plug in the y. And, so there are going to be a lot of times where we'll use like a y equation to calculate time final. And then we'll take that time final that we just found. Wake up! Wake up! Okay, that's right. I just don't want you to miss this. It's important. And then the time final that you calculate here, you can plug into the x equation. So that's why that's going to be a common strategy. All right, so let me do an example. Okay, now you can go to sleep. That's the only important stuff. Like people always come up to me. It's usually like younger, like 18-year-olds or whatever, and they're like, "I missed class. Was there anything important?" I'm just like, that does not endear you to me. Yes, I'm telling you the stuff that I think is important the whole time. Okay. Okay, so let's say that this baseball guy, uh, Joe Mauer, this is in honor of Joe Mauer's possible retirement. Yeah, did you know that Joe Mauer might be retiring after this year? He just played his last game. Do you know who that is? Okay, good. I don't really care about baseball that much, but Joe Mauer, I mean, come on. I never leave myself enough room for the head. Okay, that's like glove, baseball pants. Okay, so let's say that this baseball guy checks this ball. His arm comes up here. He releases it there. And then the ball takes off there. And let's say that at the instant the ball is released, it makes an angle of 25 degrees with the horizontal. And let's say that it's released from a height of 1.5 meters. And let's say it's released at the ball has a speed of 40 meters per second. How far will the ball travel horizontally before it hits the ground? Okay, so let's just go through the steps. So the first thing we have to do is choose those. We have to choose a time equals 0 instant, a time final instant, and then a location and orientation of the coordinate system. So I'll call that origin location and coordinate system orientation. Time equals 0. What would you guess that's going to be? Time equals 0 is going to be when the ball's released, just like it would be in a 1D problem. Time final is when it hits the ground, and both of those are based on where you have information and where you want information. So time equals 0, we're choosing that because we know information about the velocity at that instant. We know information about the position. And so we want to use that. Time final, we have to choose that to be when the ball hits the ground because we're looking for information when it hits the ground. And so that instant needs to show up in the equations. And then this is how I'm usually going to choose the origin location. So the origin location is going to be on the ground, right beneath the object at time equals 0. And then the coordinate system is going to be oriented with the y-axis up and the x-axis horizontal in the direction of motion. So if I draw this coordinate system, it's on the ground right here with x pointed that way and y pointed that way. And so when we try to calculate, when we calculate positions, the way I describe the position vector, define the position vector was it's the vector from the origin to the object at that instant. But notice that's the same thing as just saying it's the coordinates of the object. Yes. So why is it that's supposed to be where it's released. Like he's not ready to let go of it here. Yeah. His arm comes up and then right here he lets go of it. And so if we're trying to, so the star represents the instant time equals 0. The position at time equals 0, which is, that's our PI vector, so we need that, are just going to be the coordinates of that star, the coordinates where the ball's released. So what's going to be the x component of the initial position? 0, yep. And what's going to be the y? Positive 1.5, because you start at 0 and go 1.5 in the positive y direction. Okay, so the second step, we're going to list out what we know and what we want. Do we know time final? So that's how long it's in the air. No, we don't know that. Do we need it? Well, if we can get by without it, that's fine. I think in this problem, we are going to need it. We're going to find out that we need it as an intermediate variable. Like I said, that's pretty common, but for now, we'll just leave it out. Do we know acceleration? Yeah, it's free fall. And so anytime something's in free fall, the acceleration is 9.81 down. Down to us is just the y direction. the negative y direction, sorry. So yeah, our acceleration vector, ax is 0, ay is negative 9.81. The initial position, we know that, we just talked about that. So pix is 0, piy is positive 1.5 meters. Do we know anything about the final position? Yeah, so we know one thing about it. We know that the y position is going to be 0. So pfy is 0. We don't know the x position. We don't know how far it goes horizontally, but that's what we're looking for. So down here, pfx is what we're trying to find. Yep. That was given in the problem. It's 1.5 meters from the ground to where the ball's released. It's not given in the written part of the problem. Yeah, maybe that's confusing. Uh, so the ball's thrown from a height of 1.5 meters. And the angle is 25 degrees above horizontal. Okay, now the velocities. Do we know anything about the velocity when time is equal to 0? Yes. And if we, okay, so we're going to be able to calculate both of these components. And the way we're going to do that is we know that we're given that this velocity vector has a magnitude of 40 meters per second and that it makes an angle of 25 degrees above the horizontal. So this is 40. This angle is 25. And now if you put the tail of that vector at the origin of the coordinate system, then that initial velocity vector is the magnitude, 40, times the cosine of 25. And then the y component is 40 times the sine of 25. And that comes out to be, for the x component, 36.25 meters per second. And for the y component, 16.90 meters per second. Any questions about calculating that initial velocity? And then what about the final velocity? Do we know anything about that? No, and actually, there is one thing that you'll recognize in problems like this. We're going to pretend we don't know anything about it because it makes the equations work out better. But it turns out that since there's no acceleration in the x direction, there's no change in the horizontal component of the velocity, in the x component of the velocity. And so what we would see if we calculated the final velocity at the end of the problem is that the final velocity is going to be the same as this, the x component, not the y component. Because gravity affects the y component of the velocity, but there's nothing there to affect the x component except air resistance, and we're ignoring that. So really, like in our heads, we know that VFX is 36.25, but just don't write it down because it'll confuse you, like when you go to, it can sort of lead you astray when you go and look for equations that have the right number of variables and stuff. Okay, so this is the final list of what we know and what we want. So now step 3, we're looking for an equation that has pfx in it and everything else in the equation is known. All right, so let's go back and look. So first of all, we need one with pfx in it. And of these 6, there are only 2 equations that have pfx in it. So right away, we have it narrowed down to 2 equations. It's either this one or this one. And then if you look through these 2 equations, let's see, what do we need? So we need everything else to be known, and we don't know time final. So that one isn't going to work. And then this one, we don't know the y component of velocity. So we don't know so this is the one, this is why we leave off the fact that, like, yeah, really, in our heads, we know that this is going to be 36.25. But if you tried to use this equation, that would make it look like this equation was going to work. But if you tried to use it, this whole thing, this would go away because of this being equal to 0. And the whole thing would like fall apart. You wouldn't be able to use it. It would just be a waste of time. So the fact that we didn't write down VFX means that we can't use this equation either. Okay. Any questions about that? So what we found is of these 6 equations, there are none that have PFX in it, and everything else in the equation is known. So none of these equations work. Okay, none of those work. So what's the next step? The next step is to try to calculate time final and then then go back to step 2 and see if that changes our situation, you know? Okay, so now go back to what we know. Now we're looking for an equation that has time final in it. We're not looking for PFX anymore for now. We're looking for time final. Is there an equation that has time final and everything else in it is here? And I think the one that'll work is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. Okay, time finals there. That's the one we're looking for. Everything else is known. So let's start filling this in. PFY is 0. Oh, and by the way, starting now, you don't have to keep putting your units in your equations. So I wanted to do that for a little time to see how that worked, but now you can just keep this stuff as, like, now we're experts, so now we can be sloppy. That's the idea. Okay, so 0 is equal to PIY, 1.5. VIY is 16 point something, 9. Time final, and then plus 1/2 times negative 9.81 TF squared. And so you get 0 is equal to, I'm going to rearrange this as negative 4.905 TF squared plus 16.9 TF plus 1.5. We want to solve for TF. Does anyone have an idea how to calculate that? What? Quadratic formula. Yep. So this negative 4.905 is A, positive 16.9 is B, 1.5 is C. Um, and so there are two answers to that. Time final is equal to negative B plus or minus square root of B squared minus 4AC all over 2A. And anybody who has a TI calculator, come talk to me sometime when I'm not busy at lab and I can just real quick, it'll take 30 seconds or something, program in the quadratic formula so you never have to enter that stuff in. It's nice. Um, and it'll just spit the two answers out. Um, and if you calculate this, in this case, you get time final. What? The projector was on for too long. It's cooling down. Please wait. So if you plug those numbers into the quadratic formula, you get two answers. 3.53 seconds or negative 0.086 seconds. Which one of those two do we want? Yeah, we only use positive time, so we want that one. We don't want that one. Okay, are we done? No, because that's not what we were asked for. But now the idea is, go back to what we know and what we want. Um, back to step 2. And now we know TF. So we know it's 3.53 seconds. And we know all the other ones, they still stayed the same. We know the accelerations. We know the initial position components. We know the y component of the final position. We want to find the x component of the final position. And we know the initial velocity, both components. Okay, so now is there an equation that has pfx and everything else in it is known? And now that we found time final, there is one. We can use this one. Pfx is equal to Pix plus Vix in final plus 1/2 Ax time final squared. So we have 0 P, no, that's what we're trying to find. Pfx, yeah. So Pfx is equal to, this one's 0, plus Vix was 36.25. TF is 3.53 plus 1/2 times AX. What's AX? 0. And that's an easy that's an easy mistake to make, is to put in the acceleration of gravity in for AX. So be sure you keep those two components separate. 0. And so this term goes away. And we just get that Pfx is these two things multiplied together, which is 127.96 meters. We did. Yep, we couldn't have used that equation without finding t. Yep. Any other questions about that? Well, so yeah, that's a good question. It'll get the steps you follow will probably become shorter as you get used to this. I would recommend writing out all those steps to start with, and little by little, you'll just get to the point where your brain sort of does the steps automatically, and then at that point, like you don't have to write any of this down, you know. So like writing out the variables, and stuff, um, writing out what the coordinate system is, probably in not too long, you won't do all that as explicitly, but um, it can still be sort of tedious. I mean, and it doesn't take as long if you're not explaining the steps, like a problem like this won't take super long in a couple of weeks, but this is the process you have to do. The question is just whether you do some of it internally or whether you write it all out. Yep. Hmm. Negative. Yep. And negative 9.81 because our positive y direction is up. Um, so those two things are just independent of each other. Um, Here's, I guess, so if let's say this is up, this is down, okay, and we've chosen a coordinate system. Let me draw it in green. We've chosen a coordinate system with our positive y axis, right? The acceleration of gravity is a vector, has a direction and a magnitude, whether we define a coordinate system or not. So let's draw that in here. And let's put the tail at the origin because that's the way to come up with vector components. So, okay, it's a downward acceleration with a magnitude of 9.81. And um, now all we're doing is trying to come up with the components of this vector. And um, if you think of this as like one of the vector problems, practice problems that you did, this is a pretty easy one. It's a vector with a magnitude of 9.81, directed totally in the negative y direction. No component of it is in the x direction. So this is just going to be 0, negative 9.81. Or if you wanted to figure out that angle, you could go positive 270 or negative 90 and call it 9.81 times cosine and sine of 270. And you get the same thing, 0 for an x component, negative 9.81 for a y component. And what that says is that gravity is not acting at all in the x direction, and therefore gravity doesn't have any effect on what's happening horizontally. It only affects what's happening vertically. Any other questions? Okay, so I'm not going to get into this, but um, I just want to get this down in your notes, and we'll talk about this first thing next time. Um, so this is common misconception number 2. Um, So people often think that um, erase that. I could say this better. Um, that the x components of um, directional quantities affect the y components and vice versa. Um, the truth is that the x and y components are completely independent of each other. And I'm going to give you an example that sort of brings out like how this is kind of counterintuitive for most people. Um, totally independent. Okay, so let's imagine we got these two guys. Back to back. And one guy's holding a bullet and the other guy's holding a gun at the same height. Bless you. That guy, oh, I like that look when my thing was there. Uh, so this guy just drops his bullet and this guy fires his bullet. It has to be horizontal though, so let me do that. Which of those bullets hits the ground first? Um, they do both hit at the same time. And I think it's a pretty common intuition to think that there's something about the fact that this is fired with a really high horizontal velocity that keeps it from hitting the ground as fast. But the truth is, um, if this is fired horizontally, that's an x component. You know, it's not, if you think of this as a vector, it's right along the x-axis. It doesn't have any component of motion in the y direction. And so the y component of that initial velocity is zero, just like the initial y component of this velocity is zero. And because of that, this bullet is going to hit the ground at exactly the same time that this one does. It's going to hit the ground really far away, you know. And so as um, so for all, like, if there was a wall there, it would look like, you know, if you did this here in the room, this person drops the bullet, this one fires the bullet towards the wall. By the time this bullet hits the wall, it doesn't even look like it's dropped at all. So as far as you can tell, it looks like it's going to go horizontally forever. But it's not going to go horizontally forever. It's actually, its altitude is decreasing just as fast as this one is. Okay, and so that can be sort of a confusing thing. And I'm going to show a video next time of that. Yep. if you graph, so now that we're in 2D, a position versus time graph, you need to break up into an X position versus time and a Y position versus time. We're not going to do that too much, but that's how you'd have to do it. And if you graph the Y position versus time, those two would look identical. That's right. Any other questions? Okay, that's it.